Up to this point, we have looked at systems of equations which represented two lines that intersected at one point. Those were the consistent systems. We need to look now at how we can solve algebraically for sets of parallel lines, inconsistent systems, and for dependent systems where you're looking at two different equations that represent the same line. It's not always that obvious looking at something graphically because there might be slight differences between the lines. They might not quite be parallel even though they look like it, or they might not quite be the same line even though they look like it visually. So you need the algebraic tools. You need to use the tools you've been developing in order to find out for sure whether you have a consistent or an inconsistent or dependent system. And so in this segment, we'll look at how we can use our tools, focusing on the method of elimination, to solve inconsistent and dependent systems. Let's start with an inconsistent system. We'll take the system, negative 3x plus y equals a negative 1, and negative 9x plus 3y equals 4. And usually the direction you're given is just to solve the system. So we'll use the elimination method on this. It's kind of looking convenient for that. Our first step is to multiply with a strategic view toward the second step of adding. Well, if I could have a positive 9x here, when I added these up, the x's would go away. So I can do that if I multiply the first equation by a negative 3. So let me do that and rewrite the equations. Negative 3 times a negative 3 will give us a 9x times a negative 3x. Negative 3 times y will give us a negative 3y. And then negative 3 times a negative 1 will give us a positive 3. Our second equation we'll just copy over. And now we're set to add. Well, the x's go away, so I have 0. Negative 3y plus 3y is also going to go away, so I have another 0. And 3 plus 4 is 7. The last time I checked, 0 did not equal 7. This is a false numerical statement. Whenever you get a false numerical statement, you have an inconsistent system. And so you can say that there is no solution. Inconsistent. And that simply indicates that you have parallel lines that never intersect. If you were to solve this by substitution, you would also come up with a false numerical statement. Let's look now at what would happen if we solved a dependent system. So we'll take the example of the system 5x plus y equals 2 and 10x plus 2y equals 4. Now if I'm really on my toes, I'm going to notice, hey, the second equation is just the first equation multiplied by 2. But let's go through the whole process of the elimination method and see how it works out with a dependent system. It would be really nice if I had a negative 10x in the first equation. So let me accomplish that by multiplying the first equation by a negative 2. And again, I'll just rewrite them. Negative 2 times a 5x gives us a negative 10x. Negative 2 times y, we'll have plus a negative 2y. And negative 2 times 2 equal to a negative 4. We'll copy over the second equation. 10x plus 2y equals 4. And we're ready to add them. Negative 10 plus 10, 0x. So we can just write the 0. Negative 2y plus 2y gets us 0, and negative 4 plus 4 also gets us 0. Here we have a true numerical statement. 0 is indeed equal to 0. And whenever you come up with a statement like this, you are working with a dependent system, and you have infinitely many solutions. Infinitely many, which simply means they're the same line, and so all of the points are in common between them.